let's begin. All right. And what I want to do to start with is start with writing the Hamiltonian for a many electron system. So the problem we have after is many electron problem. Okay. And initially, what my emphasis is going to be on is the how do we go about getting as exact an answer as possible. Yeah, then we make approximations. So when I write about many electron problem, what do you understand by many electron problem? Let's begin right from the basic. Anybody who wants to say what do you understand by many electron problem? I need a response. I don't have a gun. If you say something wrong, I'm not going to shoot you. I'm not even grading you, so how does it matter? I'm not judging you. I'm not doing evaluation. What do you understand by many electron problem? There should be an interactive form. So that's why it becomes difficult, right? So what we're going to write is Hamiltonian for many electrons, which is going to be summation I minus 1/2 del square. By the way, I'm going to use atomic units and therefore arbitrary units. My h cross is going to be mass of the electron, going to be electronic charge is going to be 1 over 4 pi epsilon 0 or 4 pi epsilon 0 equal to 1. Okay? And so this is for each, and I'm going to write plus or B, and I'm going to use B external, which is external to the electrons, right? So this is the usual term that is written external R on each I, and plus a electron-electron interaction term. Ri Rj summed over Ij prime, so that I is not equal to J 1/2. All right. So even before we do that, why is this a tough problem? Why do you think this is a tough problem? Anybody can respond from the other side also. What makes it tough? Why people talk about many electron problem?
Wave functions cannot be like separated.
Wave function. So how does that make a difference? I have powerful computers, right? I can always give it to them.
Large number of electrons.
Yes, that we know. What is the problem? If I have the most powerful computer in the world, solve it. So let's look at that. All right. So what I'm going to do for the time being, I'm going to ignore that part. Okay. Begin with just build up with single electron problem. So let's just first ignore the Coulomb interaction. Okay. And just focus on this. When I look at the single electron problem, right? So I'm going to erase that. Oh, I have a new duster. Guess what? I'm now ready. For the two pens also. So I'm ignoring it. All right. I ignore this and write only the single electron problem. And that is this. H equals summation I. And I'll write in longhand. So I/2 will square I plus V external Ri. And as somebody remarked, I'm still after the wave function psi R1, R2 all the way up to Rn equals E psi that. So somebody remarked that separation of variables, because of this term, I can do separation of variables, and therefore I want to emphasize this point. For these particles, non-interacting particles, I can write this as a product phi1, R1, phi2, R2, and so on, all the way up to phi n, Rn. and then I solve the problem and I do separation of variables, the standard technique. So I get for each, I get minus 1/2 L square plus V external Ri phi I equals epsilon I phi I. Is that okay? All right. Now so far so good. Now if I get, how do I solve this? So there are exact solutions available. How many exact solutions do you know of where I can solve it analytically? Anybody from across the air? What all? I want to know how many problems do you know of?
Online people.
I'm listening. Tell me. Let's count that. 1D, 2D, 3D, whatever you can talk about. Exact solutions. What does that mean? Yes or no? Talk.
Like these the things that we know about.
Yeah, the ones whose exact solution analytically you can obtain. How many problems can you think of? Huh?
So obviously if I have one
Okay, 1D box. 1D box. And that immediately also goes to 3D box. All right, infinite box. How about finite box? Finite box. What else? Harmonic oscillator, all 2D, 3D. One D, 2, 3D. What else? Hydrogen atom. Yes. Huh? Step potential. No, but I'm talking about bound states. So let's write bound states. All right. Hydrogen atom. What else? Anything else you can think of? Huh? Rigid rotator. Fine. That's like hydrogen atom, so that is no problem. Rigid rotator. Right? Anything else? Anybody from across the ocean, so to speak? Anybody has any more suggestions? Somebody may know more. I'll like to learn about it. So that's where we stop. What do you do for other potentials? Or even single atom, single particle is a problem. What do I do for other atoms, other systems? So let's go here. So now let's take some other potential, right? Some P external or arbitrary. Right, so 1D I can plot some crummy potential, right? Let's say this is 0. What do I do? What do I do for this? I think इसका आवाज नहीं आ रहा. Yeah. Sound is coming, but I can't hear it. Maybe is it loud enough?
So online people, are you able to hear?
Can you hear us?
Can one of you
Please unmute yourself and tell us.
Yes, ma'am, we can hear you, but the visibility is a little bleak.
Okay, but from your side the audio is bleak. I'm not hearing anything from you. Tell me.
Across the ocean, you are the people who are across the ocean. So when he is saying he's
So okay, so now the question is, what do I do for a Fermi potential like this?
Approximate methods.
Approximate methods. But I want an exact answer. Huh? Exact. Exact answer. अभी तो exactly बात करेंगे. Exact to whatever extent you can get.
So you can map it to a matrix problem and get the eigenvalue.
Yes, that's like variation, right?
Yes.
Yeah. So what I would go right now, I said most powerful computer, solve the differential equation. That'll be the most exact one. In a way, I mean, he said matrix. So what you do is in a way, you can make a matrix and diagonalize, but or you can do solve the differential equation. Now, when you solve the differential equation, you make a mesh, right? So I'm making a mesh. So let's say I confine my system, right? All the way from this. At some point, you'll say this is wave function goes to 0, this is infinity, and let's say I take a mesh of n points, right? So I store my endpoints and I can solve each orbital by orbital and store my thing, right? Is that clear? Right? I'm solving a differential equation. If it is in 3D, I can still manage it. Now imagine if I have an interacting problem. So I'll come to that in a minute. So I can make an endpoint mesh and I want to keep it there. Then I can solve orbital by orbital. Right, so every time I just take an endpoint and do it. All right. Okay. Now, other method is then variational principle. We'll talk about in a minute. So I assume some form, right? Maybe a form which is large here, then the density goes down, and then minimize, right? Or a variational principle also you can do basis expansion. That is also variational. The important thing is that you have endpoints. Now let's go to. Or still, I want to spend some more time on this. Now, when I wrote the wave function as a product wave function, I wrote the wave function as a product wave function. Psi R1, R2, Rn is equal to product of phi I, Ri, right? There are two things missing in this. Have I taken care of all electron variables? Spin is missing. The spin coordinates. And symmetry is missing, right? So if you like, if you right now for the time being, I ignore spin, my wave function still should be antisymmetric because I'm talking about fermions. So what I form is something called the Slater determinant, right? So even for non-interacting system, my true wave function is going to be this determinant phi 1 R1, phi 2 R1 all the way up to phi n R1, phi 2 R2, phi 1 R2, phi 2 R2 and so on all the way up to n particles phi n or phi 1 Rn, phi 2 Rn, last one will be phi n Rn. That makes it antisymmetric if I switch any. You can also write it as transpose of this, the same thing. Determinant remains the same, right? Question is, number one, it says it's antisymmetric. Does it take indistinguishability into account? Yes or no? How? Hmm? Yeah, there's nothing. There's nothing. Each electron does not have an orbital assigned. I can't put a mark on it, right? So all I can say is one electron is at R1, some electron at some time, right? One electron is at R2, and so on. All right. So this is indistinguishable, and therefore symmetry anti-symmetry part is taken. If you have bosons, you just make a permanent out of it, which is plus sign, right? So this is the true wave function if there's no spin. If you introduce spin, right? So if you have spin also, then with each spatial orbital, I'll also have the spin assigned. So for each, I can write, I'm going to define something called the spin orbital, which is product phi r and the spin part, which could be alpha ms phi r beta ms, right? I'm going to define alpha and beta in a certain way. These are discrete variables. So my wave function alpha ms is equal to 1 for ms plus 1 half equals 0 for ms. The matrix representation, if you like. Beta ms is equal to 0 and 1 for ms equals plus half, ms equals minus half, right? And I'm going to call this my spin orbital chi as a function of x, okay? Where x now would be the space variable and the spin variable, right? And integral over x would mean summation ms integral of. Then everything is written. Now, for each given orbital, even if this is ith orbital, I have two spin orbitals. So they are now two quantum numbers. Right? That's the spin orbital. So if I take spin into account, what do I have? I have my wave function psi Slater determinant, which is going to be 1 over root n factorial pi 1 x1 pi 1 x2 pi 1 xn, all the way like this, pi 1 xn pi 2, oh, it should be pi n, x1 pi n x2 all the way up to pi n xn. Is that okay? Just non-interacting. I'm writing it very, very explicitly because a lot of time, a lot of people have a confusion that only if you have interacting electron, you write Slater determinant. This is the true wave function even for non-interacting particles. Whatever properties follow, they'll follow from this. For example, I can just write from here. There's something called the Fermi hole. Even for non-interacting particles, it exists. I'll talk about that in a minute. But is this idea clear? What we're doing, right? Let us take an example. So I'll leave it here. I'll erase this. If I take an example, if I take two electron system, for each orbital, I can put one up spin, one down spin. So mathematically, I would write psi x1, x2 equals 1 over root 2 pi r1 pi r2 alpha ms1 beta ms2 minus alpha ms2 beta plus 1. That's the wave function. True wave function, round state, phi is the round state orbital, true wave function for a 2 electron system. Okay, this you can see is a slated term. This is nothing but this is 1 over root 2 phi r1 alpha. That's the first orbital, right? So it will be ms1. I still write the first orbital. So phi is, except that the variable changes, r2 alpha ms2 phi r2. Now this is beta ms1, and second orbital phi r2 beta s2. Is that okay? So we are being consistent. It's always good to go back to whenever you get confused, go back to two particle system. I also want to bring out something more, and that is this. Suppose, so here there is no choice. Given two electrons in the same space orbital, they necessarily have to have opposite spin, right? So, and this is known as a singlet. Why? Because if you calculate the total S, which is S1 plus S2, S square will come out to be 0, MS will come out to be 0. So 2S plus 1, there is no splitting, is 1. Singlet, right? Now if I take another thing, just remind me of formula, I'm going to come back to it. Just keep talking, then maybe I'll forget. Oh, well, I should stop and see if there's something from across the ocean. Any questions from your side? At least say no.
No, sir.
Okay, thank you. Okay. If I have, suppose, phi 1 and phi 2, right? Then I have a possibility that both electrons could be in the same spin, right? I would have 1 over root 2 phi 1 alpha ms1 phi 1 r1 phi 1 r2 alpha ms2. Still it will not be 0 if I take phi 2 r1 alpha ms1 phi 2 r2 alpha ms2, right? This would come out to be 1 over root 2 dual phi 1 r1 alpha ms1. First orbital is phi 1 r1 alpha r2 ms2, and the corresponding slated term. So that's fine. This ms value will be 1, s square will come out to be 2, s plus 1. This is a triplet state.
Why all of the spin indices are alpha even?
Because I have two different orbitals, right? If I have two different orbitals, there are many possibilities. So many possibilities are, very good question. So I have two orbitals. So let's write the possibility. This one is, this particular state is two orbitals, phi 2, phi 1, both up spin, right? Other possibility is both down spin, right? Then I would have corresponding beta here, right, for the down spin. Does that answer your question? Anybody else has a question from across the road, across the ocean, across the river? Okay.
No, sir.
Okay. Now, other possibility is I could also have in this, I want to make a point through this. I could have these orbitals, one up, one down, right? Except I can't write like this. I have to write phi 1 R1 alpha ms1, right? Plus, okay, fine. Let me not write like this. I really need spin orbitals right now. Phi x1, phi 1 x2, phi 2 x1, phi 2 x2. Slater determinant would be this. However, if I want an orbital that has ms equals 0, right? I'll have y1 r1 y2 r2 minus y1 r1 y2 r2, and the other part will be alpha ms1 beta ms2 plus alpha ms2 beta ms1. This cannot be written as a Slater determinant. The point I'm making is that once you bring, even in non-interactive system, you bring the symmetry in. This is I'm bringing in the spin symmetry, right? Spin symmetry because I'm writing ms equals 0. The other would be this with a minus, this with a plus. One of them would belong to s equals 0, which we have already seen, right? And one would belong to s equals 0 again, but s equals capital S equals 1. So you cannot always write this. This is known as the symmetry dilemma of Hartley-Fock here. But so you cannot write everything in a single statement. If you are talking about the ground state, yes, not always. Okay, just wanted to make that point. That's why I went to this. That's I'll leave for you to work out. So you try to write it as a statement.
The ground state of the non-interactive.
This is not ground state. I'm writing two.
When you said states can be written as always as a KBT level, or that's for the ground state
Ground state.
of the non-interactive.
There's no problem. Okay. All right. So
particle it's easy to calculate. For two particle it's easy to calculate the states. For the three particle you want to calculate the other, like not the ground state, for the other states. How to calculate?
okay. So you have to make permutation combinations. For example, if you say I have three particles, right? So three particles. And how do we keep s equals, say, three particles? I could have s equals 3 halves, one half, right? So if this is actually the whole notation in this angular momentum algebra. If s equals 3 halves, you can come through to two roots. You can, oh no, s equals 3 half is okay. You write all three up. But s equals 1 half, I have two roots. I can come from s equals 0 for two particles, and combine third one. Okay, this will also give you 1 half. This will also give you 1 half. You make all these permutation combinations, and you have to actually specify the particles. That's become difficult. So that's why most of the time what you work with is Slater determinant. Don't worry about the symmetry at that time.
There are three particles.
Yes.
There are like three factorial number of combinations.
Yes.
Are there.
Yes.
Using Slater data, we can calculate one. That
One.
means
So that will be an approximation that will not satisfy the symmetry requirement of this pen.
there are 5 possible combinations are also.
Yeah, whatever you do. So you'll have to make different combinations. You have to work it out. Okay. Even I think the ground state also, if you want to do satisfy spin at the odd number of electrons, there will be a problem. Right. So that's why you kind of assume certain things even when you do Hartley-Fock, or even if you write this. Okay. All right. So that's that. Now let's come to. So these are the points I just wanted to make about even with single particle, there are a lot of things you can do. And I also want to make for me work right at this point because I want to emphasize that Fermi-Hole is not a property of interacting systems. So let's take the Slater determinant and we'll assume I can write this I1, a Slater determinant wave function. Okay. I can ask for single particle operator expectation value, right? Which is like expectation value of Fi, where Fi depends only on single variable. It could be kinetic energy, it could be the external Ri, or it could be the density. Density operator I'll write as summation I delta R minus R. Alright? Each delta R minus Ri gives me the density for ith particle at point R. And I sum over all i's, I get the total density. That becomes the operator. And this is very easy to prove if I take the Slater determinant, okay, of the single particle operator goes over to summation I OI the sum over. Alright. Both sides are the same. Okay, by the way, these are writing in shorthand, these are known as common rules for calculating expectation values with respect to Slater. Okay. Basic thing in all this is that for single particle operator, it doesn't matter whether you write a product wave function or oscillator determinant. However, if I take a two particle operator, in this case there will be only one two particle operator, and I'm going to write this as P2 R prime, which is summation delta R minus Ri delta R minus Rj summed over I and j, I not equal to j, 1 over n. And I should put a factor of. Oh, that's fine. Huh? This is what? This is correlation. Charge. Yeah. This is, I'm asking what is the probability of finding one particle at R and one particle at R minus. Right? So if I have probability of finding one particle, it's going to be this, summed over this. Probability of finding the other particle is going to be summed over j. You have removed the I, you just multiply them. If I take the expectation value of such an operator with respect to Slater determinant, now I'm taking the same Slater determinant, no orbital has been replaced. This comes out to be I. When I write I, it's going to be with R. When I write J on the left hand side, it's going to be with R prime. Okay? O2, so summed over Ij. So this is going to be summed over Ij. O2 is going to be now with respect to R and R prime.
Phi of Ri.
Phi of R. Just give me a second. No? I'm going to get a function of R and R. So this is going to be phi of R. And it's going to be R. Phi I, Rj, or Ri, Phi j, Rj, minus sum over Ij yi, ri, yj, rj, O2, y, I, rj, yi, yj, ri. And in this term, the spin of ms I is going to be equal to spin of msj. Because although you have flipped over, the term will be zero because this does not depend on spin unless their spins are the same. Okay? So this is known as the exchange term. This is direct term. Right? And you calculate it for this. Calculate it for the Slater determinant. This comes out to be rho density at R over N times 1 over N minus 1 rho R prime minus summation I j ms equals mj yi r yj r prime star yi r prime yj r. That's it. I can write this m also. M is symbolic because I've taken away this symbol. All right. This I can write as rho r over n rho r prime over n minus 1 1 minus this whole thing divided by rho. Right? You with me? This derivation I'm doing. Main thing is focus on this idea. Now, if he said this is a correlation function, this is a correlation function. Because what is happening, this is giving me a probability if I take one electron at R, what is the probability of finding another electron from rest of the minus 1 electrons? Okay, what it tells me, if the particles were all independent, there was no symmetry, no indistinguishability, they were just moving around as if the other one did not exist, then in this whole milieu of particles, this is bothering the hell out. It's not. Alright? Probability of finding a particle somewhere would have been just density divided by n. Do you agree with that? Right? There's a density and divide by n. For the other particle, it would have been rho r prime divided by n is the probability for one particle, n minus 1 divided by n minus 1. So this would have been the density for the rest of the particles. This would have been plainly this. Just product of two densities. Yeah, one is going one's own way, the other one is going one's own way. What is happening now? I still have this. I'm dividing by n minus 1. The probability is getting modified. So here it was the whole thing was one density. Suppose I just assume at some point and expand at some point, right? Here. This was the density. Here's my electron. The other particles, the density is not the same. I'm subtracting something. Right? And I'm subtracting it. Since I'm dividing by n minus 1, the whole probability has to be 1, right? That's what this has to be. Rho r, yeah. Thus, there are n missing some. If I integrate this over r prime, right? This actually comes out to be 1. So probability is getting resolved by, okay. Just one second. I'm finding the probability of particle at r prime given a particle at r. So this is 1. Just give me a second. Messed up some nice sign somewhere. This actually you can show this is this. If you integrate this, this comes out to be 1. Okay, so this exclusive, what gets excluded is exactly 1, except that, just one second. That rho r prime, no. I think I'm, this would have been, yeah, now I, when you get a product, you get rho r prime, and I took this rho r out. This is sorry about that. Would have found out anyway. All right. Now this is where it comes out. I didn't mess up. So this below is like this. Now it makes sense. I had a rho r prime. If there's a rho r plane, rho r prime would have been constant. But I'm subtracting a quantity. Right? And that quantity is this. And since I'm dividing by n minus 1, this whole thing integrates to 1. This better integrate to n minus 1. So this whole thing, rho r prime minus this animal, dr prime is equal to 1, n minus 1. So this thing, which I'm subtracting exactly 1. Charge normalization. That's the math part of it. If you interpret it, what is happening when you made this antisymmetric wave function? Each electron is moving around with this deficit. If I locate one electron, there is a deficit of electrons. And since this was MSI and MSJ equal, that means only parallel spin electrons create this deficit. Suppose this is upspin, downspin will still come here. But parallel ones, deficit comes. So it is as if an electron is going around with a hole around. I have to stop here and see if there are any questions. Well, this is a very important concept because if I include correlations of Coulomb interaction, this hole becomes deeper, bigger, and all that. But this is a very important concept. That antisymmetry of the wave function keeps parallel spin electrons away from each other. Are there any questions from far away?
I have a question.
Yes.
This correlation.
Yes.
So in general, can I take it to be transmission invariant? So it depends on two quantities, R and R.
Yes.
It will depend on. So can I say in general it will be a function of the difference of R and R?
That's right.
If I plot it as a function of as a function of difference, then I should see a low value or maybe zero value at difference equal to 0.
For the same spin, yes.
For the same, but for the
Opposite
other
spin will come.
you-
So this has exactly value the density divided by 2,
so half would be
half the electrons.
see half at 0 if you're opposite.
Right. Yeah, but there's no interaction. It's purely a Pauli correlation effect. Each electron is moving around with this deficit. this is known as the Fermi hole. This quantity is Fermi hole, which integrates to 1. And I want to emphasize this because we are then going to interpret exchange energy in terms of this. Any questions from candidates online? No, yes? Okay. So is this point clear? Right? And this comes only from symmetry. It has no other effect right now. That's it. All we are saying, even in this non-interacting system, each electron is moving around with the deficit of parallel spin electrons, and that integrates to 1. It excludes exactly 1 electron. All right. So that's the setup for non-interacting. Can I erase all this? Do you have a question?
Maybe may I ask one more question?
Yes.
This Fermi hole.
Yes.
Suppose, of course, you arrived at it by assuming the stated determinant.
Yes. Yeah, for non-interacting, it is related.
I get it, but you also said that even if you bring in interactions.
Yes.
The point is that is this a general feature? Will it always be there, irrespective of whether you can write them outside the statement?
Yes. I'll come to that. That's what I'm coming to now.
But in principle, even from non-interacting, it should be there, right? Because it comes because of the symmetry.
It comes from this line.
Yes.
Yes, this is non-interacting. So for we might include correlate with the Coulomb interaction, it becomes a little deeper. It has no extra.
So your point is that even without interaction, only exclusion of Fermi only statistics is forcing a correlation, absence of.
Sir,
Yes.
we have a starting point, we have a part electron at point R,
Yes.
position R. We are going to find the probability of another electron in position R prime.
That's right.
And what is the result of this? Like the whole Fermi rule is I like Fermi rule, I don't understand from straight to answer.
Okay. So what I did, I said that. So let's start with this. Suppose this is a gas, and I'm taking a particular point, and I'm expanding it. Huh? I would say that I've located one electron here, and then its density kind of is maybe varying, but it's very microscopic point. So there's this density, and I want to locate another electron next to it. Okay? Somehow I forced it here. I forced the other electron. If there was no correlation, the probability would have been rho r divided by n would have been the probability of finding one electron. The other electron would have been rho r prime, and for n minus 1 electron, the density would have been this, right? And for probability, I divide by n minus 1. It would have been just product of two things. What I have when I introduce the Slater determinant, I don't have this. What I have is rho r by n, 1 over n minus 1, rho r prime, minus this divided by 2. This has developed a structure. Probability has a structure. Here, I subtracted one electron, that was the density. Here I subtracted through this. But this subtraction now is not a mere shift by constant something. It has a structure. Okay, and that's the problem. And it comes from mixing all I and J. So this is correlation between electrons and different orbitals. They are somehow correlated, all the parallels. Is that okay? Does that answer your question? Anything else?
What is the shape different?
What is it? The phi wave function, right? For example, if you have all the plane waves, if I take a homogeneous electron gas, right? Then what will be my phi's? Phi's will be e raised to ik dot r. This comes out to be a spherical Bessel function. There you can calculate exactly. These are easy. For others, you have to calculate. The shape depends on how your density is changing, how phi is changing. This is not a universal shape.
Can this thing be related, or is this then cause of degeneration? Starting from here, can we arrive at the equation?
No. Degeneration pressure is always exclusion principle, right? I mean, this goes builds up. You have all the particles moving, even at zero temperature. They give you pressure. They cannot be all in the same order. So you can say, okay, Pauli exclusion gives me this, Pauli exclusion gives me this. But can I calculate pressure from this? The answer is no, I don't know. But it's easier to calculate, just take the kinetic energy and calculate. It's just a correlation function between two electrons. Any other question? Yes.
Related to that, we take care of two and anti-symmetry that two electrons will come together. Like still you get some positive solution. And why we are worrying about
Fermi hole.
yes, and it's like why are we making assumption that spins comes together?
Okay, very, very.
Deficiency.
So you're walking in the market, suddenly you look at somebody is wearing red, shiny shirt. You look at it, right? And you're curious. I want to know what the property is, what does it do? Different properties. All we are saying is if I look at two electrons, they keep away from each other if they're spinning. How does that away? Is it that keep away from me and I'm just away from you, or does that have a structure? We are mathematically finding out this is a property of having an antisymmetry.
I guess you also partially answered the question is that when you talk about how the Coulomb interaction
That's
depends or
that's
changes this.
anything else? I'm glad there's a discussion. Anybody from the other side? Okay. I'll tell you what. So I also sit in a lot of committees and interviews. Sometimes I mute my mic and go off to sleep. Probably, I hope you're not doing that. Don't use my trick. Okay. Now let's. So this is that. Now remember what we have learned. We've learned that you have n single electron problem. Slater determines the wave function, and even in 1D, if I have n particles, right, I calculate n orbitals, and there are n mesh points. I mean, particles could be any, but n mesh points. All right. If I have two particles, I'm still solving for n mesh points. Now imagine this. Hamiltonian is minus 1/2 del square. I'll write it as this. Right? It's still one dimension. How many mesh points would I need now? Square. So if I had 100 mesh points here, which is a very coarse grained calculation, I need 100 square. I have 10 particles. 10 raised to 20 points. I have 10 raised to 23 particles. To make a computer as big as the universe. Can't do it. I'm going to require.
Classical. Classical.
Yeah, classical. We only quantum can do only one particle, right? Even
Yes.
one particle. All right. So that is the answer. That's why it's a very interesting problem. You cannot, even with most powerful calculator or computer, you go to 7-8 particles and you take it. Memory requirement just becomes so obvious. Okay? You need other methods. It's just impossible to solve. Well, so is that point clear? Is that point clear from across the thing? Across the universe. John Lennon saw.
Sir, can you please repeat?
Yeah, so we went over, even if I have a two particle system, if there is this term R1 minus R2, right? Since I
Yes.
cannot do a separation of variables, my wave function is going to be psi, even if I take one dimension x1, x2. If I had n mesh points for one particle, I need n square mesh points for two particles. N raised to 3 for 3, n raised to 10 for 10 particles. And I immediately run out of memory. So even if I
Yes.
have the best computer possible, I cannot solve interacting problem even numerically. That's why one needs to develop methods. Okay?
Fine, sir.
So basically, the number of coupled equations start increasing.
There's one equation.
Couple equations when you have the hard to solve.
I don't even have coupling.
Still, you are like,
Yeah,
okay. So just because of
I'm dead. Finished.
This is called exponential function.
Exponential growth. It's going n raised 2. So immediately 3, 4 particles, that's it. You have reached your limit. Okay? That's why I need to develop other methods. Okay. Now we'll come to interacting part. Okay, so let's again start with particles. Then we generalize it. And again, I'm going to first focus on ideas, right? Okay. So I had, let's make a simple picture. Particle in a box, all right? Non-interacting. So both particles could be in this ground state, right? This is sine square. By the way, a few years down the road, you're going to go to faculty interviews and all that. Always make sine square x with this. A parabolic at the end. A lot of people make it straight. Boom. Then they get hassled. Okay. It is parabolic. Okay. Now we made this, and the highest point is 1 because sometimes people write something else. Therefore, this guy goes up here. That's science. Now I introduce interactions. Just thinking out, right? So I introduce interaction. What do you think is going to happen with this density? Simple two-particle density. What are the particles going to do to each other? They're repelling, right? So what do you think? How do you think the density is going to change? Mega? Make what? That's why I said come in front. Are you coming in front? I can't hear you.
Symmetric and anti-symmetric.
Louder. You see what you're making me do? Ah, symmetry? Let's talk about street talk. I mean, symmetry will be two bombs. Huh? Two bombs, okay? Two bombs. Yeah? Why?
They will be localized far from each other as they are of same spin.
That's a lot of talk. Let's first talk, make the curve, and then we'll talk about it. Spin there up and down. I took the system, all right, and I suddenly, so let's call this lambda. This is lambda equal to 0, and suddenly I decided let me make lambda equal to 1. Right? So what do particles do? They say let's run away from each other, right? So they make two bonds. Is that okay? Does everybody agree with that, or are there any disputes? Now you can make your longer point about symmetry and all that. What were you trying to say?
Yes, they will repel each other, so they will want to stay far away from each other. That is why two bonds are far aside from.
Yes. Yes, that's the point you're making, right? Understood. Now, so this is the density. How about the wave function itself? I'm talking about only one dimension. Just want to develop an intuition. So suppose I still want to write the wave function, right? I cannot solve it. So let's guess a wave function. right? So initially it was sine kx1. Let's write k. सब कुछ सही करेंगे exactly. Pi over L x1 sine pi over L x2. Okay. Somebody would say you didn't do things right, so I'm going to write this also. Where L is the width of the box.
What?
2 by L. Root 2 by
No,
L.
no, you are right.
I said somebody is going to say you said. Okay. But I'm glad I was not on the wrong side. Generally, I'm on the other side. So. Okay. How do I modify this wave function? Because now I know I cannot solve it. So let me try to build a wave function. Let's build our intuition. And I also want something from the across the, from far away. I can't throw you a chocolate if you give the right answer. Usually I do. I'll get you guys chocolate next time, next lecture. I'm seeing who's talking, who's not. Modify, simplest possible. Have you heard of Occam's razor? Huh? Occam's razor is start with the simplest thing. Probably that's the right.
Maybe counting the number of bumps.
Yeah. So let's now we're doing that. See, that's the problem. The problem is this I face always in the class. When I give mathematical argument, people say, sir, physical argument. When I ask physical argument, sir, mathematics is over there. Right now I'm just asking for the intuition, physical intuition. And just put in some math. You're not giving me mathematical argument or a function. But I could guess that nobody is going to kill and see best thing about doing theory is nothing explodes. Theory you can really do things. Let's write, let's modify. So this was lambda equals 0. Let's do lambda equals 1. Simplest. You said they're going to repel. He said they're going to repel. Let's put a repulsion term. And the probability of them being close together, is it less or more compared to this? This was maximum here. So you see, you will be able to do things if I make something out there. What you want to do is, the probability out here has gone up. Here it has gone down. Total number remains the same. This is what you have made, right? Let's modify the wave function so that it becomes something like this. In the simplest possible way. What do you think you want to do?
So e to the power minus x1 squared,
E raised to minus
x1 squared plus e to the power minus x2 squared,
x1 square plus
to the power minus x2 squared.
but you violated Occam's razor. Went so far off. Because you see, if you want to get this, you better keep close to this. This suddenly, and this is not becoming 0 at the boundary. You have to satisfy the boundary condition also. So can would you mind if I cut it off? You would? You would not. Okay, so let's cut this off.
Yeah, so you have to.
You can put in inside the state. I mean, like,
Yeah, that's or increase the period, like double the frequency of the.
So let's write it.
Yeah, so cycle
It's not okay with me.
Okay.
We should have fun also,
Yeah,
right?
sure.
Let's just show.
Yeah. So one guess could be again. It can be
Yeah, so guess.
2
Because we'll keep guessing and then reject ideas. See, this is the way to do science. If you reject all wrong ideas, you're left with the right idea. You have to keep doing things.
basically introduce higher Fourier component.
Okay, so what you're saying is
Just one guess. No, I mean,
there's no problem.
Yeah.
Yeah, guess it. So we'll analyze them scientifically. So here is the thing. Here is the thing. And you said, let's make the wave function like this.
Yeah.
Double the period. Right? So I have this, I have this, I have this, I have this.
no, but so or you can have just sine 2 pi Lx1 sine pi Lx2.
Isn't it like the first one, lambda is equal to 0 is you're putting the, I mean, think of that you have different levels, energy levels. You are
Yes.
putting first two particles. The first equation is putting, or the first wave function is putting particles in the same state. Next one
add
could be
sine
higher.
pi by L x1.
Add.
Add a sub.
So let's go that is systematic, right? I cheated you when I wrote lambda equals 1. So No, wait. कर लेते बताना हाँ बोलो.
We need something like delta like peak at 2.
I know what I need. I want it from you.
So then delta like function 1 by x squared plus.
So you are saying what? So let's write it for lambda equals 10 raised to minus 5. How do I modify it? थोड़ा सा करते हैं. Now the modification will be very little. How do you go about it? Then I'll go to lambda equals 10 raised to minus 2. Then I'll go to lambda equals 1. And I'll keep building. And you see, this is where now I'll come to what he said and what he said. What he said and what he said, right? Intuitively, what did you think? Why did you make 2 bumps?
Existence of 2 particles.
No. System of 2 particles was there also. There was no bump. They're repelling each other, right? So what they're doing is, that's why I made this picture. They're repelling each other from here, and they're going away. Can I just add a term to make them repel?
Can be like minus of some parameter times sine pi by L.
Wait. Now I want to spend time on this. You want to write minus
Some small parameter times sine of pi by L x1.
sine of,
Pi by L x1. Sine of pi by L.
but all you have done is change the normalization. You renormalize it, it comes out to be the same, right?
Can you shift x1 and x2 by some?
Give me a function. I mean, all that I can also talk. That's what I'm saying. I got to do this. That we already know. I want to keep them away, right? So let's write this. Probability goes down if x1 minus x2, doesn't matter which way, is close to 0, right? Probability goes up if x1 minus x2 is as far as possible, but then they also reflect from here, right? So I want to do this. Let me multiply by a function that does this, right? And still satisfy the boundary condition. This is a fantastic function to satisfy boundary condition. I don't want to touch that. That's why I said go simply. Okay. Anybody from the other side? I think they have all gone off to sleep.
So maybe try a
So e to
function.
the power minus of x1 minus x2 whole square.
Okay. So you want to multiply it with this?
The first function you have written with a blue ink, and then it is multiplied with e to the power minus x1
Okay.
minus x2 whole.
So I'll erase this, and then you multiply this by
E to the power minus x1 minus x2 whole square. And when
and I put a parameter here.
is whole square. Sir, x1 minus x2 whole square.
Gaussian of x.
Whole square. Well, if I'm putting the mod, then that doesn't matter.
When x1 and x2 are very close, then it is nearly equal to 0. And when there is a huge gap, then
It's going down. That's one possibility, right?
Yeah, probably we want 1 minus of that.
Yeah. So now there are possibilities. So you can write 2 over L, whatever, the normalization will change. Sine pi over L x1, sine pi over L x2, 1 plus maybe beta x1 minus x2, or the powers or exponential, whatever. Trust your intuition. When you're doing physics, trust your intuition. That becomes a very good wave function. Now we have a parameter called beta. Now, when you make a wave function like this, anybody has any questions, comments from the other side?
No, sir.
Okay. So when you have something like this, I put a parameter beta. Besides that, you also want to modify, certain, so those theorems, you say, who wants to read this one? Read those theorems that have been proved. You want to satisfy exact properties as much as possible. I'll come to that. Even when you do numerics, if you know some limiting answers, for example, one limiting answer I know is the boundary condition. So I don't want to touch this. I want to modify it, right? I want to modify it in such a way that they move away. and then I have a parameter beta. So there's no problem. How do I determine beta? Now I have variational principle. Right? Now, this does not go all the way. Classically, these two particles would have sat here. Right? Classically, if I take this particle in a box and take these two particles, they would have gone and sat on the corners. Isn't it? Why are they coming maximum in the middle? Why is that? Why do you think bumps are not? Why is this wave function not right in the corner?
Yeah, you have answered this.
That's there's always the kinetic energy, so they come close to each other also, right? This is the kind of intuition I would like you to develop when you're doing many-body theory. Many-body theory is nothing. It's just we make a big deal out of it. It's very simple. Develop that intuition, way of thinking. Okay, you see, so easily we wrote the function. Now you have the variational principle, right? So I'll come to the variational principle. And that probably you all know very well that I have a Hamiltonian, take the expectation value psi with this parameter beta and do this. Variational theorem says that it will hit a minimum. This will always be greater than or equal to the ground state. Right? There's a standard proof in shape and everything, and you determine your beta. Lower the energy you get, better your wave function is. Right? Now I'll answer his question that he asked initially. Now you see, if we were to somehow in 2 dimensions, oops, in 2 dimensions, suppose I were to plot this wave function as x1, x2. What is this wave function doing? It's going up here and coming down. It's like the surface is like this. Dip out here. Compared to when they were non-interacting, there's a dip. So compared to when if I were to plot the 2 particle wave function, 2 particle correlation function with 1 electron located here, it has a hole around it. It is keeping away from each other. That's the correlation. There, the parallel spins were keeping it away. There, the electron-electron interaction modified the wave function so that they cannot come close together. If they cannot come close together, that means there is a hole around it. That's the correlation. And by the way, I made it. So let me just give it to you. In any system, if I were to calculate the probability of finding 2 particles, it will be rho by n. I'm just now thinking out loud, all right? 1 over n minus 1 rho r prime minus, earlier was exchange, now I'll write exchange correlation hole for an electron at r prime. Is that okay? Now, earlier we had seen that rho x r prime, this we could see mathematically as well as by argument was exactly 1, with excluding 1 electron. If I apply the same conditions, after all, I'm calculating probability, and I'm saying probability gets reduced by this. This will also be 1, right? So although there is a correlation hole, this net charge is 0. But still gives you some energy. Okay, so that means if I would just calculate effect of Coulomb interaction on the hole, this net charge is 0, but it's much deeper out here and the thing gets compensated. We'll come to that when I discuss this more. I keep coming back to this. I wanted to make a point. Is that okay? All right. Do we take a short break, 5-minute break? Let's take a 5-minute break. All these concepts we take to DL. So we are going to take a 5-minute break. All right. 11:30, 11:35, 36 we will start.
a two-particle problem. For the initial one, when we are finding the densities, and rho is divided by L. For the second particle, as we have already fixed one particle, that's why we are
Ready my minus 1 now. So if they were all independent, right? Suppose in this room right now we have 50 people. One of them walks away and I say average density, just shift by 1. Will remain like that. Right? Or if there's a structure, you move away, other people move out. Then there'll be a structure. That's the structure. Right? Not a silly question. Any other questions? We have a sister in IIT Kanpur, Nanda. Yeah, you look exactly like her. The twins. Her daughter. I came there and I said, what is Nandita doing here? And I realized no, one of the friends.
Maybe I have a question.
Yeah.
So, of course, we are treating lambda to be positive. If I make lambda negative, suppose a bound, but then I would expect the bound state to act as an independent particle and still have a sort of sign square kx distribution. Okay, like a single particle which is now.
Yeah, so in that case, I'll go the other way.
But will it increase the bump at the center, or will it? Because I don't expect that bound particle to stay at the center. That will also.
Okay. What you're saying is okay.
So I will, in that case, my intuition says you will still get a, kind of like sine square kind of thing, which decays.
Yeah, so boundary conditions will still be the same.
Still be the same, but it will.
So maybe it will
resemble
become
the sine
flatter.
I don't know. So it could also be a matter of lambda hitting a critical value. Below a critical value, the shape will be different. So
Maybe that name.
one more thing. For the first exchange part, we are not included the Coulomb interaction. Means the lambda value will still be. Then only you have the whole.
That's why I did it in non-factor, yes.
But here for getting the whole, we have to increase the lambda from finite.
Yes, there are holes, and the two holes are for two different reasons. In one case, you are making a slightly determinate wave function. So it tells you that only if spins are parallel, the density gets reduced a bit. In this case, no matter what, right? They're going to keep on it. Right? Is the picture clear?
Parallel they will far apart. That means we have to include the Coulomb interaction in that.
Then it become even deeper changes because now it's rho xc. So it could so happen I made a hole there, right? So I made a hole which was, let's say, like this, and this excluded exactly one charge, right? I could now have slightly deeper here, but then this extra has to be compensated because net is 0. So do something like this. All the positive parts add up to all the negative parts. You have a much more interesting structure. Does that answer your question? Anything else? Okay, so let's begin now. Okay, now what we are going to say, so we have come to the point that wave function gets modified. One case is later determinant. If you add correlation also, it gets modified, right? And so let's see now. let's talk about helium atom, the simplest two-body problem, right? And so can I assume that you know variation principle? Right? So what we have said so far is that we assume a form of the wave function right based on intuition or make a better word, better than intuition, insight into the problem. Insight is very important. For that, you got to have this picture, right? How the game is doing this. I can always tell the computer do this. That's not fun. Can you tell me some one or two very good insightful wave functions? Fractional quantum Hall effect, the guest wave function, because you can't solve the interacting problem, right? Huh? I was coming to that, but I wanted to start the other. Right? So those are the insightful. So you do that, put in some parameters. With respect to which you will minimize. Alright? And I said you want to take some things into account. So for example, I'll just go step by step. Helium atom. First thing you can say is that maybe because of electron-electron interaction, there's some staining and the wave function still remains a product wave function. But it is not as tightly bound as it would have been otherwise. So I call this, whatever the coefficient are, e raised to minus some z effective r1, e raised to minus z effective r. So it's slightly less bound. That's one guess. Right? It will make electrons go farther away. Right? And you take in the expectation value of the Hamiltonian. And this answer is well known. For all two electron systems, z effective comes out to be 2z minus 5 over 16. Okay? So that's one way of looking at it. Now, you can keep building physical intuition. Second thing you can say is, so in this case, what I did, I said both electrons are in the same orbit. Does not take care of effect that we saw earlier, that electrons keep away. Okay? They are moving in some sort of Z effective, which takes care of this electron-electron interaction by subtracting from the Z. Is that right? On an average. Right? So here what I'm doing is I'm making something called the mean field approximation. If we think of all mean field and everything, this is what mean field is. In some sort of an average way, each electron is seeing the same. Is that point clear? It is different from what we said earlier in the case of two particles in infinite box that they are keeping away. Right? I can go better than that. I'll say, no, but one electron is here, the other one will be out here. And switch. So I can make a better wave function, which is some normalization e raised to minus, let's say alpha r1, e raised to minus beta r2, but they are in the ground state. So I got to symmetrize this. E minus alpha r2, e raised to minus beta. Because I don't know which electron is where. One electron is here, and one of them will be greater than the other. Right? So what is happening? When one electron comes near to the nucleus, the other one goes away. This is now this I cannot write as a product wave function.
The ground state of the other.
Huh? This is the ground state.
So is the other.
Huh?
On the same orbital, R1 and R2.
This is now you see, this is a very good question. When two particles are interacting, there is no concept of orbital. Each one doesn't have an orbital. I'm writing psi R1, R2. And I'm using my physical intuition that when one particle is one place, are there any questions from across the from far away? Hello.
So
Hello.
thinking.
Same thing. Yeah. So when there are two particles, there are two interacting, but there is no individual orbital. Individual orbital means we are thinking of each particle moving in a common field. That's the mean field approximation. Now I'm going beyond that. So this, I'm saying when one particle is near the nucleus, the other one is far away. I'm correlating them. Now I have two parameters, alpha and beta are parameters. Okay, I can make it even better. I can multiply this by 1 plus some other parameter R12, where R12 mod R1 minus R2. Then alpha, beta, and gamma will become parameters. Right? All right. So not only are they keeping away, see in this case they were keeping away only at this distance or this distance. By introducing R12, I have also made sure that even if R1 and R2 are the same, angularly they are far apart. R12 is the distance between them. So what it is saying is keep the R12 large. So even if they are the same radius, R12 can still be large. I made it even better. This is how we build the wave. All right. Now, roughly, there's the kinetic energy T, V external energy. Then there's the energy of interaction, rho r prime over r minus r, right? Explicitly, dr prime. Then there's going to be exchange energy. There's going to be correlation energy. They're in decreasing order. They're roughly the same and then decreasing. Why do I need this correlation? We have a feel for it. It's a wave function for over 45 over here. Very important, qualitatively, even if the numbers are small. Okay? Just give you one example. Then we'll go into the math. Suppose I'll just go through simple examples. I take H minus. There's one positive charge, one electron, right? Far away, so outside the field is going to be zero. If I bring another electron, it should not even bind. Neutral charge cannot do it. But what this electron does is it pushes previous wave function like this. So positive charge is closer, and then it can get bound. This is distortion of the wave function because of the presence of the other charge. This is correlated. If there was no correlation, H minus wouldn't bind. Even the energy would be maybe 1/10 of an electron, but it's very important qualitatively. Right? Now let's come to another. Just introducing these concepts. Now I go to Hartley and Hartley-Fock theory. let's talk about molecular orbital, is MO and valence bond. Okay, let's talk about two electron system and a molecule. So I have system A, nucleus A, nucleus B. All right, these two atoms, and this atom has a wave function phi A. Suppose there's a single electron, so I'm talking about H2, phi B. Except when they come close together, they'll start interacting. All right, and what I can do is I can write the wave function molecular orbital as phi A R1 plus phi B R2 times some normalization constant C1. And I made an orbital. This is what is it known as? LCAO, linear combination of atomic orbitals. What is the solid state counterpart of it? What is the solid state counterpart of LCAO? Tight binding wave function. Just make up the block wave function with combining atomic orbitals, right? So then, if I calculate the probability R1, R2, no. So psi, this is for R1 and R2. Then I'll multiply by the other molecular orbital phi. If I just take the product with R2 plus phi B R2. Suppose I have solved and then I've made this wave function. Now, and phi A and phi B will optimize by some method like we did for heat. Alright? There's some mean field. This would be whatever that constant phi A R1, phi A R2 plus phi A R1, phi B R2 plus phi B R1. R1 phi A R2 plus phi B R1 phi B R2. If you look at this wave function, this is comprises of four parts. This part is okay. One electron is at A, one electron is at B, and the symmetric part. In this case, both electrons are at A, both electrons are at B. How would that affect energy if they were interacting? Is the energy, right? So this is one approach where this has, even if you stretch the atoms apart, there's always a probability that one electron will be there. One-fourth of the time you'll have one electron here, one-fourth of the time you'll have it. But in real life that doesn't happen. What? The electrons go, they're individuals. That happens because this increases the energy. Correlation is important. Psi MO may be good when they are close together, but it's a bad wave function. Let's look at the other wave function. Psi valence bond, in which we say that each electron is in its own orbital plus symmetric term. Yes.
I don't understand the part. If we make them far apart, then it will be difficult for them. Like first two part, first and the fourth part, we contribute less.
No, if they are right on the same atom, then phi A R1, phi A R2 means they are on the same atom. They can contribute enormously to the energy.
But there are some constant. If I write down the explicitly the wave function, it's C1 into phi A R1 and C2 into phi B R2.
Yeah, but you're writing your wave function like this, you're solving. You're making an LCAO. To approximate the wave function, you already done that.
Yes.
Now, what you want to do is this. You're saying you want to do this. That's what you're saying. But this keeps the two electrons away from each other all the time. Right? So this is undercorrelated. This is overcorrelated. Even when the A and B come close together, right? Delocalization energy is not going to be there. They prefer to be in their own atoms. So when you form a molecule, there is a delocalization. That is not happening. So this will not give you a very good answer when you're close together. This will not give you a very good answer when you're far away. Two-wave function maybe is a linear combination of the two. So IMO lambda 1 plus 1 minus lambda psi valence bond. And then you normalize. Lambda is a parameter. This is, by the way, known as a size consistency problem. You should be size consistent. If you go far away, electrons should go to their individual atoms. Or whatever normalization is. And this is known as Coulson-Fisher wave function. It's not known just like because they did this. What they did, they calculated the energy at different arcs. No problem with these.
So DP means
Valence bond. It's not a valence bond. All right. Calculated this as a function of R. All right. What they observed near about equilibrium distance, where the molecule really exists, is lambda, which is from 1 to 0. So the two-way function is really a combination of the two. Okay. This is like atoms, the electrons are floating around, they were also spending time here and there. Now they suddenly decide to sit at their atoms. Okay, this is a very interesting calculation. And what you see in solids correspondingly, I should expect the same thing. Atoms are far apart. For metal, where the electrons can move around, they should suddenly go to valence bond type. They should go to their own atoms. So if they, rather than being delocalized, they go to their own atoms, what happens? System becomes from metallic to insulator. Right? That's the metal insulator.
So we take a break at 12 for 10 minutes. And we'll have tea.
Oh, you want another break? Nobody took a break.
We did. I'm sorry. Tomorrow onwards we'll have at 11:30. But
Okay.
we'll be also getting tired.
Yeah, that's all right. So, okay. So I'll just finish this idea. So now you see this whole thing, lambda going from 1 to 0, is driven by what? What drove it? What made this switch in this wave function when I minimize the energy? Huh? What is it? Coulomb interaction. Coulomb interaction is playing a very important role. Coulomb interaction made the two electrons sit far away. Now let's go to a solid. Right? And if I were to write the molecular orbital, right? Well, again, it's again, I've been doing all ideas. So some normalization constant, which is 1 over root n, by the way, under certain proximity, nearest neighbor approximations, e raised to I k dot. This is 1D, so kx, phi atomic, x, let's say x naught, no, this is xn, xi, xi, xi. That's the time binding. That's my LCAO, linear combination of atomic orbitals. Just like we saw in two particle system. Here also, there will be a probability that electrons are far away, but sometimes they'll come close together. Maybe two, maybe three. Then cost energy. And therefore, as you go far away, keep costing energy. Reduce that energy, they should switch from coming close together to a wave function, which I'll just write psi valence bond, just roughly valence bond, okay? Which will be a product of these atomic orbitals, phi x1, phi atomic x2. It's switched, just like Coulson-Fisher wave function switched from MO to VB. The switch, right? This is and it's been driven by what? Just like in the Coulson wave function, Coulson-Fisher wave function, it was driven by Coulomb interaction. Here also this transition is driven by Coulomb interactions, right? So this insulator is not the band insulator. I mean, in a way it is because now there's only a single level, right? But the transition took place because of Coulomb interaction. It's not because of gap, right? So correlation, right?
So I have a question here. So when you say Coulomb interaction, I am understanding there are two kinds of Coulomb interaction. On between the two electrons, one coming from pi and one coming from p. And I am guessing there is also a Coulomb attraction of each electron in an individual.
That I have taken care of in phi, right, in this wave function, right? In some mean field or something. So I'm going beyond. So by mean field, I made an MO or something. So MO is a mean field thing. Now I'm going beyond that.
So, but I'm asking that the electron, suppose the electron which is originally far apart, will also be sensing the Coulomb attraction due to B as well.
Yeah. So that I have taken care of. The phi A I have taken care of somehow.
So,
Or if you want, okay, if you want them to be purely atomic orbital, I have just done that. I have not. That sense will come when I do these. But main point. So if I optimize them again, that will come. But main thing is this will dominate.
So so this is to kind of set it down for my next question. Is suppose I neglect the electron-electron repulsion and keep all the other Coulomb attractions between A and B, for example, would I also expect a switch over?
Okay, that's a good question. So if you do that, okay, now in that switchover should not take place.
At the right arm.
Huh?
At the right arm.
Should not.
Yes,
Why?
I
Once you take far apart, the effect of this goes away. They stay here.
So that would have had a wrong prediction for us.
That would have been, yeah, but I don't know whether it did it or not.
Okay.
But let's see. I made an LCAO and I do a calculation. The effect, now in that case, MO or VB doesn't really matter. Because it's not making any difference. MO and VB made a difference in the energy to interaction only. Because of this term. You see, this is finally this part, this valence bond. You're just adding these terms. Now, by optimized, probably it will remain an MO, and MO will be such that it will just. Yeah. But I without doing I can't.
Yes.
Intuitively.
No, I get it.
10 minutes, 10 to 15 minutes, not more than that. He is outside, let's have in 15 minutes we are back.
I think we ought to tell them also the other part.
Okay, they can have their own.
Yeah,
10 minutes, no? So that
we'll have a tea break for 10, 15 minutes, 15 minutes, okay, and we'll get back. Okay. Oh, I think I should.
I'll come back. I do hearty pop and all that.
Quick, we should do it quickly because 15 minutes is going good.
second one is that suppose three of you can
So there is another lecture at 3, right? All of you know?
Yes, sir.
Yeah. That would be a very interesting topic. Very informative. No plan to go back to IICS, right? And यही करो यार.
Okay. Anyway, okay, so now we have set up the basic ideas about, I mean, there's a picture in the head, what's going on. All right. Any questions so far? Okay, so now we're going to go over to the very, very Hamiltonian, which is summation I minus 1/2 del I square plus the external Ri plus 1/2 summation Rj prime 1 over Ri minus Rj. And we are going to build up wave functions, right? So you said we have to guess the wave functions. We talked about mean field wave function for 2 electrons. We've done all that. Now, the first mathematical theory is Hartree theory. Now, I want to do this because this goes directly to, we take it over to DFT also. Intuitively, what we'll say, this is a mean field theory, and I have already told you what mean field theory is. In that, we are going to assume that electrons are each doing its own thing in some sort of an average field given by the others. So, the wave function is going to be assumed to be a product of n orbitals, right? And so that's number one. Number two, Pauli exclusion is included by occupying maximum 2 electrons per orbital. This you do by hand from outside. It's not built in. Okay? If I'm assuming it's a product wave function, it automatically means, so let's write it this way, that electrons are moving in a mean field. Okay? So what are we doing? We are approximating a wave function. And I want to emphasize that because when I do a similar thing in DFT, we are not approximating a wave function. Here we are approximating a wave function. And just by physical intuition, density of all these electrons is going to be summation I occupation of each orbital mod phi IR square. This will give rise to a mean field. This mean field would be I'm going to call this Hartree, which is going to be integral Coulomb potential due to this. And I'm going to call this Hartree, okay? But each electron cannot interact with itself. So I'm going to call this V self interaction term or VSI, okay? Because it sees only the field of the other end, right? So this is going to be integration of phi I r prime mod square over r minus r prime dr prime, which I should subtract from V hearty because V hearty includes everything. So I can write the equation for each orbital, which is going to be 1 minus 1 half del square plus V external r plus V hearty minus V SI, but this is I dependent at r phi I r equals epsilon r phi I r. Is that clear? Is it okay? Say it again. SI,
Density.
this one.
Top line.
FI is the occupation. Could be 1 or 2. Okay, I'm putting the spin from outside. Is that okay? So this is fine. You solve. Now notice because of this, potential is different for each orbital. Is that point clear? Because I'm subtracting phi I, vi, right? This is different, and this is solved self-consistent. That means I start with some approximate phi, right? So I start with, important to write this, phi I, some guess, calculate VH minus VSI, solve the equation, phi I, let's write this old, new, equals phi I old, approximately you put a tolerance, stop. Otherwise you go back. Until this happens. I want to give you a calculation to give you an idea of self-consistency. I appreciate if you do it. Okay? Because we always say you go in a cycle. But what it really means is, suppose I had done that helium atom, right? So in helium atom, there are 2 electrons. We had said that there is E Z effective, R1 e raised to minus Z effective, R2, right? I'll say one electron has an orbital e raised to minus AR1, the other one has e raised to minus BR2.
Sir,
Yes.
the last time it depends on orbital, but how? So those only depends on the position. These R1 and
Yeah,
R2.
but the last term is phi I, subtracting the potential due to that orbital. So if I suppose I have a 1s and 2s, right? 1s and 2s. So when I'm calculating for 1s, I'll subtract off the potential due to 1s.
So here the potential unit 2 electrons is sitting in 1s. Two electrons they are sitting in 1s. Calculating their
Suppose I have 4 electrons. They'll be sitting in 2 orbitals, 2 different orbitals. And I calculate the potential for the first orbital. Let's say beryllium, 1s and 2s. When I calculate the potential for 1s, it depends only on the orbital 2s. And 1s ka only 1 electron. So I'm subtracting one of the electrons from 1s. For 2s, I'll be subtracting 1s. So it depends on, right?
for the last part, there the two S parts are contributing to the last part.
So let me write this. Let me write this. Since you asked, let's say beryllium, right? So I do my Pauli exclusion, 1s2, 2s2, right? I write the orbital for del square plus, minus 4 over r plus integral rho r prime over r minus r prime. Just writing it exactly in the same form. Minus 2 integral y 2s r prime mod square over r minus r prime dr prime minus integral of 2s to only 5 of this. Y 1s r equals epsilon minus. And for the other one, it will become phi 2s.
What are those? Those are the wave functions.
Those are the initial wave function I see.
Initial wave function associated with one electron. One is contributes one electron. For the two is we also have one electron.
2 electrons, 2 spins.
Two spins means two electrons. There are interaction between two electrons for the two is. For the one is also the similar thing. The interaction between two
For
electrons.
1s is also interacting with 2s. So this if you write this explicitly, this whole thing. Suppose I write this whole thing, right? I open it up. Okay, just one second. Give me a second. I open it up. What does it come out to be? It comes out to be phi 1s r prime mod square over r minus r prime dr prime plus integration 2 phi 2s r prime mod square over r minus r prime dr prime. Right?
Why I don't understand that.
How many electrons are there in the second one?
Two as well as in the one is also two electrons.
Yes, but the electron I'm solving for cannot interact with itself.
Okay.
Right? For the other one, it will become 2 phi 1 SR. This will go to phi 1 SR. Phi 2 SR. 3 electrons affected, right? Yeah. Anything else? Anybody from across the universe?
Sir, could you please repeat this last point that you just mentioned?
Okay. His question was, how do I calculate the potential? And all the point that is being made at that, for the electron you're calculating it for, you subtract its own potential. So if I'm calculating it for phi 1s electron, I'll subtract due to the other phi 1s electron. I mean, I'll add potential due to 1 phi s electron and 2 phi 2s electrons. And same thing if I'm calculating for 2s, I'll add the potential due to 1 phi 2s electron and 2 phi 1s electron. That'll be the total potential. That makes it orbital dependent.
Okay, sir.
Does that answer your question?
Yes, sir.
Okay. So equations are only 2. Maybe you're thinking 4 equations. No. Because I'm assuming the orbitals are the same. Okay. Now, okay. See, to understand self-consistency, you try this problem at home. It is very interesting. And I learned it from, Noah Laureate's book, Harbora's book. So what he says is, now these are 2 parameters, A and B. Okay? So he calculates, suppose I want to find B. So I'll calculate minus 1 half del square, Hamiltonian would be this, minus 2 over R, or whatever, Z over R, plus the potential due to e raised to minus AR. That all. This will be the Hamiltonian for the second one. Then you calculate the expectation value, e raised to minus BR, e raised to minus BR, comes out to be some expectation. Okay, let's say E, whatever B. And it depends parametrically on A. Then you do DEB, DB equals 0, gives an equation in B and A, right? And for self-consistency, after deriving the equation, put A equals B. That is the self-consistency. That orbital that you started with, I started with some A, calculated the other orbital, and then made them equal. That's what you do. Do this, because I've chosen this form of the wave function, you'll find that A will be equal to this equal to Z effective again. Because I've chosen this kind of form of the wave function. That's the idea of self-consistency. You calculate potential due to one, calculate the orbital due to the other, and try to equate them infinitely. Is that okay?
Can you repeat this?
Which part? This one.
Self-consistency.
Okay, you start with some orbital. Okay, so I'll go back and forth and you'll see. I started with an orbital. Suppose my orbital is one is e raised to minus br2, the other electron is e raised to minus ar. Here I have chosen n orbitals, right? Let's say n or n by 2 orbitals for n electrons. Okay. Now, what did I do here? I calculated, given e raised to minus ar1, I found out what e raised to minus br is, optimum, by doing variation calculation. Given these orbitals, I'm finding each orbital again. I'm making this potential. I made this potential, right? And I found this. I solved the equation. I solved the equation, found B. Then I made B equals A. Here I say B is not equal to A, go back and do it again. Clear? Anybody else has any question?
The total answer depends on the wave function. Modify the wave function, then
Also, oh, very good question. When I'm minimizing, I'm keeping this Hamiltonian fixed. That's why I did not take A equal B right from the beginning. Because then I'll be modifying the wave Hamiltonian. I have to keep the Hamiltonian fixed when I'm doing the variation of this. So I calculated with some A, which I'm keeping fixed. I'm calculating the optimum wave function for the other one, for this A. Then I'm saying in the end that for self-consistency, A must be. If I did that right from the beginning, then I'm not doing a problem. I'm doing something fun. Right? Does that answer your question? Anything else? Okay. So this is a Hartree problem. Now you can derive this variationally also. Alright? Although I did it very intuitively, exactly same thing comes, but I'll not derive it variationally. I'll derive Hartree-Fock variationally, and then Hartree is included. Is that okay? Alright. So what will be the energy in this? Energy will come out to be expectation value with this product wave function, right? Hamiltonian y I. And a lot of people make this mistake. This is not equal to summation epsilon. Okay? It's not equal to summation epsilon. Right? Rather, this will be the expectation value of the kinetic energy operator plus expectation value of the external operator. So I hardly plus the expectation value of Coulomb interaction energy operator, and that comes out to be, you can show it very easily. I'll leave it as homework. Rho R, this is the energy of interaction between two charge density, between all other charge density. dr prime, but this is including the self interaction, which I'm going to subtract. Summation I integration yi r mod square yi r prime mod square over r minus r prime dr. Yeah. I'll leave this as an exercise. Okay. So This I'm going to call the future E R3.
As
This
we
is one sec, E self interaction. Yes.
as we are using the mean field, we're able to write them as a summation over epsilon. Because
What is the energy? What did I minimize?
the this part.
Did I minimize summation of epsilon I? Did I minimize the expectation value? What does the variation principle say? The expectation value, minimum value is the constant. I cannot suddenly change gears now. Right? This is the energy, and this, then by the way, you can manipulate with the equation. This comes out to be summation of epsilon I. Okay?
This rho r's are also can be written in function of the phi.
Yes, so rho r we have already written is summation I phi I r.
Just the density.
So this is very clear. This is the energy of that density, electrostatic energy. This is the self interaction. Okay? We actually minimize this with respect to phi I, take a minimal, then you get the RT equation. So this is epsilon I minus 1/2 integral rho r prime over r minus r prime plus 1/2 summation r. Okay, so you can see smart this. Right? And this comes because if you take summation over epsilon I is the equation. If you take summation over epsilon I, it comes out to be this expectation value, this expectation value, this is without a half. pH is without a half. That half is corrected for. Yeah, and this is also without. All right. Okay, I'll leave it here. I want to keep it, and now I want to take the Hartree-Fock wave function. If I take the Hartree-Fock wave function, that takes care of the symmetry to be 1 over square root of n and all that I was writing in the beginning. Chi ix1, chi ix2, and I1 x1, I1 x2, da da da, I2 x1, I2 x2, so on. Okay. I had already told you what the expectation values are with respect to a Slater determinant. And what are we taking the expectation value of? We are taking expectation value of minus 1/2 del square summed over I. Kinetic energy, we are taking expectation value of summation I B external Ri. And we are taking the expectation value of the two body operator summation Ij prime 1 over Ri minus Ij. Alright? And I had said, if you take the one body expectation value with respect to this, it will come out to be simply summation I, Fi, I'm taking the occupation also now, phi I with respect to R, minus 1/2 del square phi I. This is the kinetic energy expectation value. Right? The expectation value of V external Ri is going to be V external Ri with respect to phi. So it can simply come out to be summed over Fi I is density. That makes perfect sense. Because the entire density which interacts with the external.
Here we are introducing Coulomb interaction, but it reduces the energy. Like the single electron energy should be summation over epsilon.
There is a single electron energy.
Like if I don't have a Coulomb interaction,
Yes.
if I calculate the epsilon values and sum over them, then I will get the total energy. Now, if we are introducing Coulomb energy, it will reduce the energy.
Where is it reducing?
Minus factor is there.
This is much smaller than this. Because suppose they are n orbitals, just a rough calculation, okay? Suppose they are n orbitals. Is it proportional to n square? This is proportional to n. Each is 1 and you're summing over n. Each is n n okay. N square minus 1 times n. And by the way, I just want to make a comment that in a extended system like a solid, this term is this is n square. You can ignore this term. Right? This is ignored as n tends to 10 tends to 20, which will mean I solve. Okay? Okay. Now, then, so is this point clear that there will be a rho r here? Can you see that? Because this will be V external Ri times FIR, FRR summed over with each occupation. This is the same, can be taken common, so you're left with only phi r square rho r. Plus the Coulomb term, integration, this is a direct term. Rho r prime over r minus r prime. And again, this is a two-body operator that I'm taking. That time two-body operator was delta r minus ri, delta r minus rj. Right now it just happens to be 1/2 ri minus rj. So it comes out to be minus 1/2 integration phi I r phi j r prime star phi I r prime phi j r over r minus r prime dr prime. Let me write sigma here. For the spin, all spins have to be the same. So you have sum over ij, sum over sigma. Ij I'm separating from. Ij is only special part, sigma is this part. Spin is the same. This, notice, if I ignore the cross terms, if I take only I equals j term, goes to this. Okay, so this includes self-interaction automatically. And I can also write this as divide by rho r, multiply by rho r. Then I can write this whole term as minus a half integration rho r rho exchange whole r prime over r minus r prime dr. That makes perfect sense. This is the exchange energy, which includes self-interaction. Okay, this is when this electron is going around, it's keeping away the parallel spin electrons. This calculates as if the density is uniform. Now it says no, but if this electron is here, the electron is going to keep away. Energy is going to be lowered with respect to that. And how much is the lowering? It is the interaction energy between the exchange hole and the electron. Count each electron, sum it up, you get a low. That's the interpretation of exchange energy. It is the interaction energy between the exchange hole. So exchange hole always existed, interacting or non-interacting. When you introduce interaction because of exchange hole, energy gets low compared to just hot treatment. Second thing, this has only self-interaction. This has little more. So exchange energy lowering is better. Okay, so Hartley Fock energy is lower than Hartley energy. Any questions so far? Any questions from across the ocean? Any questions from that side? Okay, so is this point clear? I'm doing better than Hartley Fock. I'm doing better than Hartley. And now how about the equations? So that's why let it here. Thus, everything is the same except for the last two. This has self-interaction plus more. Better look. And this is the best possible mean field you can do. You cannot do this. No matter, because I'm doing, and now we'll do variational principle. Now, since it is an approximate wave function, so I Hartley Fock going to be always greater than. I'm not even putting equal sign. I'm ignoring relatives. They're all non-relatives. and but you will never go lower than 2. And this is to make any other wave function, it will always be above 1. Any other mean field. Any questions so far? Now, what about Hartley-Cock equation? I had already written Hartley equation. Let's write. So now it is this. Is the physical interpretation clear? Okay. Now, I'm going to introduce the idea of a function. E Hartley-Fock is a number which is given by functions set by I, right? And or n by 2 orders. So this is a map from a set of functions to a number, or if you like, real space, real number, right? This map is known as a function. It is not function of a function. For example, suppose I have sine kx, right? Cosine of, so this is f. Cosine of f would be cosine of sine of kx. This is function of a function. Whereas sine, say, 2. Suppose I define f of this f, right? Suppose I define f of f to be equal to its value at 2 be sine k. This is the function. This gives a map from a function to a number. This is general because suppose I take f is some arbitrary function, say e raised to minus x, then f of f will be e raised to minus 2. So here what I'm defining this functional as is integral fx delta x x. I'm taking the function, multiplying by delta x, integrating under a number. It could also have been a function g of fx in general, a weight function, not delta x, dx. Could also do that, right? That will also give me a map from a function to a number. That's a function. Is the definition clear? And it is not functional, not function of a. Okay? Is the idea clear? So given a set of phi i's, I get a number. So it's a functional of this set of phi i's. Just like I can have a multivariable function, I can have a function of x, y, z, I can have a function of many functions or one function. Is that okay? Just like I can define a derivative in function, I can also define a functional derivative. exactly the same thing. Okay, so let's just do that. And by the way, a very good book for this, and I recommend it, is Calculus of Variations by Delphine and Homi. It's a classic, very easily, very well written, very user friendly. Okay, you'll become faculty members sometime. It's a good book to have. Very easy to read. So I have a functional derivative. Now, when I define a function derivative of a function for df, I write df dx, some delta x. I'm doing it not with a lot of mathematics, but that's how I define the derivative. By the way, functional is written with this square bracket. Whenever you see this as a square bracket, and I gave you a particular one, but in general, this is what's going to be. Okay, whatever it may be, the entire volume, it may be some boundary, it may be the space you're working. Okay. Similarly, I'm going to define a functional derivative as delta f would be given by integral. Functional derivative is written like this. And it's going to be a function of x now. So you're doing, okay, delta f x dx. All right? In a way, if you think of a functional, okay, so I'm going to, can I erase this? Is it okay? Okay. You can also think of a functional as a function of thousands and millions of variables. Because what are you doing? Let's see. I'll just go without wx. So suppose I take this function. Just doing 1D, okay? This function is like this. Whether I take a square or whatever I'm taking, I can suppose I just do fx dx. Just for the heck of it, right? Fx dx. Suppose I define my functional like this. You can do it for others also. F could be g of x, whatever. Right? This is nothing but summation of fy. So this is delta xi. And this is xr. This is. So if you think in terms of Riemann integral, right? This is a function of, suppose I divide this into endpoints. So this is a function of n variables. It's a way of looking at it, right? Otherwise, it's really that deep. Are you with me? All right. So I can think of it like this. And what about the functional derivative? What am I doing? Suppose I change delta fx. Suppose I make a specific change. I just change it right here. Right? So I'm making my function like this. So I think in terms of Riemann integral. Right? I'm getting this extra stuff. Right? You calculate this value. Okay? Then you will see delta f. Do it, that numerical product will come out to be partial. Then write g there. E by partial f minus e by x. Partial g. Partial. You didn't know this. Now where do you know it from? Huh? Lagrangian. Right? In Lagrangian, what do? You say that action is a minimum, right? And you define action as integral kinetic energy minus V dx, which is the functional of, and these are all T depends on Q dot dt, and minus V depends on Q dt. Then you say there should be a minimum. What you're saying, if there's a minimum, delta A, delta Q should be 0. Just like df dx is 0 near a minimum, maximum, right? And that gives you delta L, delta Q minus d by dt. Okay, so that's really your big getting function. The function derivative is the function. Function derivative is a function because you're varying the function at a particular point. You're saying how much is the variation. Now, there are two kinds of function derivative, get to and Fechet, but I'm not getting into that. Okay. A practical way of calculating functional derivative, if you want to do it, this will give you the same answer is limit epsilon tending to 0, 1 over epsilon, integral f plus epsilon delta x prime minus x minus f x prime. I'm going over x prime. Okay. What you're saying is, so I have this entire space, x prime, at x, I'm making this spike, right? With respect to that spike, whose strength is epsilon, how much is the functional change? That's the difference.
Can you really make a spike? Is there a condition like the difference should be very small? And make a change.
So this is a linear. So if I make a change, I'm looking only at the linear difference. Linear, just like in derivative, I look at the linear. Okay. If you want, you don't like the delta function thing, then you say, I'll calculate it as f plus delta f minus ff, and whatever comes out, I'll keep up to linear term. It come out to be like this. This will be functional. Easy way of doing it. Is that okay? Okay. So what I got to do, so now you understand this is E Hartree-Fock is a functional of these functions. Now if I want to do a minimization, right? If I want to do a minimization, what should I do? Near a minimum, if I vary the function a bit, delta f, which is delta f over delta f v r now should be 0, right? Near a minimum. So if these are arbitrary, this should be 0. So what do I want? I want delta E Hartree-Fock phi I set divided by delta phi I r is equal to 0, but I have a condition. Phi I should be normalized. Hartree-Fock, you assume that all the wave functions are normalized. I'll do that through Lagrange multiplier technique. So I'll take a Lagrange multiplier for each orbital, epsilon I, integral, I'm doing phi I. So mod phi I r square dr minus 1. That's the condition. Where epsilon I is Lagrange multiplier. If you don't like this, what you can do, this will give you delta phi I over delta EHF over delta phi r integral, right? Give me something phi I star delta phi I integral dr equals 0, but this integral itself is 0 because these are normalized, right? And it's complex conjugate. So this can be a constant. That's precisely the Lagrange.
Sir, if we have
like the energy value, if you plotted the energy value with the wave function, they don't have only one minimum. There are more minimums of the wave function.
Variation theorem says minimum is only one.
Then we have more than a
Huh? You cannot have more than one. You have degeneracy. Degeneracy is minimum is unique. At least system has to come somewhere. Okay? So that variation theorem says. Now once you have this, now I've given you the formula. I'll just quickly write the answer. So what you get is for phi I you're going to get minus 1/2 L square plus V external R plus V hard 3 operating on phi I R, that's fine, minus integral phi I star R prime phi j R star phi I phi j R over R minus R prime P R prime summed over J, all sigma the same. Right. Yeah. Yeah, summed over J, and they should only over those orbitals are sigma the same. This would be, this is not being summed, only J is being summed. This is parameterized.
For one, for any orthonormal, phi is not a like a wave function.
Okay, this is a wave function. Okay. So what you're saying is that I have taken only. So his question is, I've taken only that each orbital is normalized. There's one more condition. Actually, I should be doing this. That's what he means. Yi, yj, dr equals delta ij. That's what, right? If you do that, you're going to get epsilon ij. You can show you can do a transformation. Then you can diagonalize it. Some cases you cannot, but in general, you can. Okay? So I'm already assuming that I'm doing only this condition. If it is spin compensated, then there's no problem. If it is not, then you run into some problem. But you can say that I'll treat all the orbitals the same and do something called the restricted part. Okay. So now,
So can you repeat the explanation?
no, in general you should have epsilon ij, phi I, phi j. But I'm not worrying about that. All I'm ensuring right now is that only phi I r square be normalized, which in the spin compensated case you can show through a unitary transformation that can be done. Is that okay?
Okay, sir.
Now, if I take only I equals j term, ignore rest of the j's, you will see that this is that self interaction. This goes over to Hartley term. But now I'm including other j's. So it's interacting with all the parallel spins, not just itself. So it includes that interaction. So this is beyond Hartley, going to Hartley form. Except that this is a non-local integral. This is of the form, I'll call it Vx r prime phi I r prime. Phi I should be r prime. That's okay. R interacts with phi I r prime and phi j r prime. Yeah, this is phi I r prime dr prime, where Vx r prime is this integral. Vx r prime is this summation over Vx r prime. Let's write this. Vx r prime is phi j star r phi j r prime over r minus r summed over j. This is a very funny integral. It's acting on phi all over the place, right? This is also to be solved self-consistently, except that now it becomes more difficult compared to Hartree. Okay, so what do we have? If I write the Hartree-Fock equation, I have minus 1/2 del square plus V external R plus V Hartree R acting on phi I plus integral V exchange R prime phi I R prime dr prime equals epsilon I.
It's more like a delocalized, I mean, electron shared between the I and J. And that is
Electron,
the R prime electron.
yeah, so
I mean,
it's not acting locally on this, it is acting all over the place.
Yeah. But it's more like a shared. So I and J are included. I mean, I and J are. So there's a sum over all J.
Sum over all j. It's interacting with all the electrons. Interacting with all the electrons. In Hartree theory, it was only self-interaction correction.
So this is more on like a sum over all the orbitals.
It's sum over all the
Orbitals.
j is all the occupied orbitals with the same spin.
Same.
It's interacting. Its potential is being affected by all the electrons. Whereas in Hartree theory, it was its own interaction vectors.
Basically, it's more like a hopping term, right? Considering or the orbital orbital overlap.
Orbital overlap, yeah, let's say that. Yeah,
So in some sort of same density.
but I think more of it, this guy gives rise to a potential. Even if it did not overlap, potential will still be there. Even if one orbital was localized here, one orbital was localized here, this guy is still going to. Yeah.
That's why it's confusing.
Okay, so I think having derived this, I think I'll stop here. Okay, now we'll start from here and then do Thomas Fermi, time dependent Thomas Fermi, and that will take us to DFT. Next 4 lectures.
Sir,
Yes,
sir, could you please explain that Vx r prime phi I r prime dr prime? I mean that curly bracket expression. You are standing next to it, sir.
this one,
No.
No, sir. No, sir.
this one.
Yes, sir.
Okay, so here I have written, for 1 sec. Here I have written phi I r prime, phi j r, and integrated over r prime, right?
Yes, sir.
This term I'm writing as Vx r prime. Just by definition.
Okay.
Okay, and I'm integrating over r prime, so it's not acting locally on this. If it was local, this would have been proportional to a delta function, delta r minus r prime. So that's a thing. So it's not acting right at r, it's acting all over the place. Does that answer your question?
Okay, sir.
All right.
Isn't it like just having the one R is sufficient? Just R prime. Here is the
No, I have integrating over r prime. So, and there's an r. I need, because there's a phi j r.
there's a
Phi j r.
so actually
If this was pure r prime, then there would be no r dependence.
yeah. So the denominator will have
Best you can have, there is a delta function. That'll make it work.
So while doing some real calculation, suppose that there is no external potential.
Yes.
So this Vx r and r prime turn out to be something on form.
Yes, it will come out to be constant. In fact, I'm going to do the homogeneous electron gas calculation where the maximum potential is taken to be constant. Even then, this term would shift the potential down.
I'm asking you about the form of Vx. Like in the calculation, does it turn out to be like Coulomb? Is it 1 over r minus r?
No,
Because effectively what is happening, like one is feeling the effect of all of the others because
Yes.
of the Coulomb effect.
Yes.
So this potential should also look like
No. So okay. Okay. Here's the answer to your question. One, it is acting all over the place. So how do I decide what does it look like? Even if I so it's acting on this. What you're saying. So I'll tell you why you're asking this question. You're asking this question because here you see everything multiplying. It is like 1 over r minus r prime. Or it is more like we take a localized system far away, it's 1 over r. It is not clear. If I take it far away, then it will be minus 1 over r because I can take this r out, right? Or even then there will be a 1 over r minus r prime. So it's a little funny thing. Okay? It is Coulombic in nature, all right, but its behavior is non-local. It depends on both, so you can't really separate from them. Does that answer your question? Anything else? Okay, so we stop here.
Any other question from online people?
Any question from online?
No, sir.
Yeah, so everyone, so 3 o'clock, same place.